Hey guys, hello and welcome back to my channel. I recently got something in the mail that can only mean one thing. Yeah, here the TDU PCBs for a new TDAC build video that I'm working on are ready. NANI? Wait, these are not the ones. That's for another video. These are the TDU PCBs. Not sponsored, by the way. And yeah, this means I can start working on the video. I've been a build video of the TDAC that I've been thinking about for a very long time. So it's nice that we are finally able to start with that. However, my goal for that video is to make it way shorter than the collective series. My idea is to get it in one video for the actual build, the physical build, and one video for the software part or firmware part, however you want to call it. And to do that, I'm going to have to assume some things. So my idea for that video is to explain each part of the build, show a little bit what I'm going to do, and then show the afterwards. So if I have to solder some wires, I will explain I'm going to do this and then do that off camera and show the image. That way I can shorten the video much more. However, that means I'm going to have to assume that the viewers know a little bit what I'm talking about, because I'm not going to be going step by step and showing every single solder joint that I do, obviously. But I'm going to assume that the viewers know a little bit of what I'm doing beforehand. And there's one aspect of the build that I think I need to talk about. I can't just assume that everybody's going to know how it works. And so that's what this video is for. I'm going to try to explain. So how are we going to put the almost 80 digital inputs that the TDAC has and 4 analog inputs into this little board here, which only has 18 input pins, input and output pins. This is a Pro Micro knockoff. And yeah, you may say it's difficult to do that because, yeah. So there's several ways to do that, and I've built several TDACs already, using different techniques. The first one that I did is by designing this. This is a matrix, button matrix PCB that I designed. This is very similar to something like this, which is very common in Arduino kits. This is a keypad, right? And if you notice, it has 4x4. This one has 4x4 buttons. So that means a total of 16 buttons. However, it only has 8 pins. That is because this is a matrix, a button matrix. I don't know if you can see that properly, but the buttons are connected both in rows and columns, right? And this is how a matrix works. You connect the 4 pins for rows and the 4 pins for columns. And when you press one button, the program knows that you're pressing, knows which column and which row are you pressing at the same time. So it's, if you press 5, the Arduino detects that column 2 and row 2 are being pressed, and that's number 5, right? That's how matrix works. However, there's an issue with button matrix, which is called ghosting, that when you press more than one button at the same time, so you would have ghosting issues with this keypad if you were to press some of the keys at the same time. So it doesn't happen always, it depends on the combination, but if you were, for example, to press 5 and 6, I don't know exactly if that would trigger the ghosting, but if you press 2 buttons at once, it might understand that you are also pressing something else. So for example, I think it would do it if you pressed 5 and 9. Maybe the system would detect that you're pressing 5, 9, and also 6. I don't know exactly if that is the case, but you can do some more research online about ghosting issue. And to avoid that, what you do is you use diodes in each junction, right? So in each of these junctions here, right, you use a diode to avoid current from flowing to a different input. However, although I did design this PCB with diodes in them, I'm just a hobbyist, and I did something wrong, and I still have some ghosting issues sometimes with this option. This is an 8x8 matrix, and actually 8x8, it's 64 inputs. So actually it did have to be 9x9 to have 81 inputs, but that covers all the pins. That's 18 pins, and that would cover all the pins in the Pro Micro, so you wouldn't have analogs available for it. So what I did is not only used matrix PCB, but this matrix PCB, which you can see the rows and cols pins here, was actually connected to a port expander that has 16 pins that you connect to the Arduino BO2 I2C pins. So that was getting too complex, and it was also failing anyway. So what I did is, I'm using already port expander, which I started with PCF 8575. It's one of the options that you have. I didn't like those at all. I had them failing quite often. So I moved to this one here. I don't have any at the moment. This is an MCP 2317. And as you can see, they are very, very inexpensive. So what I did is get the number of these expanders that I needed. Instead of just using one and the matrix, I thought it would be way easier to just use as many expanders as I needed for this project. And it's actually not that many, it's 4 of them. You will need 4 of these port expanders if you want to build it this way. I was explaining this option just so you know my history with it, but just don't do it. It's not worth it. So using one of these, what I do have is same thing. This is a different version of the MCP 23017. It just has a different format, but it's exactly the same thing. This is a really good option. It's not my preferred option, and I will explain which one I do prefer later, but this is perfectly good. I've had several TDACs built with this option and works perfectly fine. I've never tried this version. I always had these ones here, and they work exactly the same. But what I liked about these ones against these ones is that if you know anything about port expanders, if you use more than one, you need to set a different I2C address for each one of them. So in this case, we're going to be using 4 of these boards, and you will need to set 4 different I2C addresses for them. And to do that, there are 3 pins in this board. You cannot see the pins in this picture, but on the bottom side, there's prints. There's markings for each pin. There are 3 pins that are marked as A0, A1, and A2, and those are not analog pins. Don't get confused with that. Those are the address pins, right? So if we see here, you can see here the 3 pins, A0, A1, and A2. By default, both in this board and in this one, they are connected, as you can see, to ground. This gives it an address of 0x20, right? So with a combination of connecting these pins to VCC, so for instance, if you connect A0 to VCC, and you would do this in this particular board by moving this 0 ohm resistor to the VCC pin. So there's 3 pins here. It's ground, in this case ground to the left, VCC to the right, and you cannot see it, but this 0 ohm resistor is connected to the actual A0, A1, and A2 pins on the right side, right? So you would move this 0 ohm resistor to VCC and the middle pin. That would mean that the address has changed in this case to 0x21, right? And depending on the combination, so if you move A1 to VCC, that's a different address. If you move A1 and A0 to VCC, that's a different address. So, and if you do that, you have 8 possible combinations, right? That's the number of port expanders that you can actually use. You can use a maximum of 8 with their different address combinations, right? And what I liked about this is that you just need to move this resistor to the side. With this one, you have, I believe, A0, A1, and A3, 2 pins are these 3 pins on the top right, I believe. And then you have some VCC pins. I don't know if it's here or here. I think it's somewhere here on this side. So what I had to do, it's not too big of a deal. I mean, it's not a problem. It's just easier to do it with the other board. But you would need to connect a wire from A0 to VCC, for instance. And what I would do, since I need to connect a wire, I need 4 of these. I would leave one without connection, which means it's the default address 20. Connecting A0 to VCC, that would be the second one, that would be 21. Connecting A1 to VCC, that would be 22, sorry. And then connecting A2 to a VCC, that would be address 0x24. So we would have 20, 21, 22, and 24. And I did that because otherwise, if you want to do 20, 21, 22, and 23, 23 is actually connecting A0 and A1 to VCC. So I would need either 2 wires or connecting the wire from A1 to A0 and A1 together and then to VCC, something like that. It's not too big of a deal. You can do that, but it's just easier to connect each pin to VCC once. And since you only need 4 addresses, that's how I did it. In this case, I can do whatever because it's just a matter of moving this 0 ohm resistor around. But just for consistency, I'll probably just do the same. So this will be one of the boards, and that's 20. I'll move one of them from A0 to VCC, that would be 21, A1 to VCC, that would be 22, and A2 to VCC, that would be 24. That's just the best, the quickest way to do it, right? And with this method, you have to upload the sketch that I have in the website, the Arduino sketch, using the Arduino IDE, and you will have to do some minor adjustments to the code that I will display in the software video when the time comes. It's not that you need to code, you just need to make small changes, and I will tell you which changes you need to do. It's not difficult, but bear in mind that you will not have like a proper user interface. It will be a code that you will need to change and adjust and understand what changes are you doing. But it will be pretty well explained in the video when I come to it. So my last option, the one that I did, and actually the one that I'm going for afterwards for any device that I build, unless I need to do it differently. But for the most part, this is how I'm gonna go from now onwards, is using shift registers. Shift registers are also some sort of port expander in a way. They do allow you to add inputs using just a few pins on the board actually. So for the port expanders, you usually need 4 pins and including VCC and ground. So you use VCC, ground, and then 2 other pins of the board, of the Arduino board. For this, you use 5, so you need 1 more, right? But it's still a very good option because you can daisy chain, as far as I know, 8 of these in line, and each one of them has 8 inputs. So a full chain of shift registers. By the way, this is a 74HC165 shift register. If you daisy chain 8 of these, then you do the math. That's 64 additional inputs, right? And that's how I'm building my my devices from now on. I prefer this because, for one, is what you would find in a commercial device. Like if you open up your HOTAS, you'll probably find shift registers used in there. It's the way to properly do it. These port expanders are more like for DIY projects, and you wouldn't find them in commercial items, although it's perfectly valid and it works perfectly fine. But yeah, this is the way to go. The problem with these ones, there are several problems with using shift resistors, and let me tell you which are. These boards are very, very readily available, very inexpensive. As I showed you earlier, one of these, you can see they sell for $1 each, or around that price tag. These ones are not as easy to find, and they come in very few options. So this one that I'm showing in paper is because I've never gotten one of these. I've never used them, and the reason I haven't done it is because they are not as cheap. As you can see, these are $5.49. This is from AliExpress, and they do not. I haven't found them in Choice, so you also have to pay the shipping. So, and you will need 3 of these for this project. I found out that getting the 3 of these for with shipping included, that was about 22 or 23 euros, something like that. And another thing that I didn't like about this is that, as you can see, they come with 3 chips. This is actually not 1 shift resistor. This is 3 shift resistors in one. So this board, as you can see, you cannot in the description, okay, it's cut. But this shift resistor, this board allows for 24 inputs because it's 3 chips in one. Something I don't like about that is, for one, they seem chunky, bulky. I don't know if this would fit. I think they would probably, but I'm not sure if they would fit inside the collective grips. Sorry, not the collective, the TDAC grips. And also, if you count only the number of chips for this project, you actually only need about 7.5 shift registers. That means that you need to buy 3 of these, and that would be 9 chips. So you're gonna have a lot of leftovers, and they are not that inexpensive. So that would be paying more for something that you actually don't need, and you're not gonna be using all of the pins, right? So there's another option, which is this one. Focus, yeah. This is exactly the same chip, but it comes in a single version. These are very inexpensive as well. I believe these are like $1 or something like that. And as I said, you're gonna need 7.5, so 8 of these boards. However, these boards have what I consider a flaw. These ones don't have this flaw. So these ones are ready to work. You just connect them and they work. But for these ones, there's an issue. If you see, so you have these are the connections that go from and to. So for instance, this is serial out, as you can see. This is the side that connects to either the Arduino or the next shift register, right? Because as I said, you can daisy chain this. So if you have two of them, you would connect the serial out of one to the serial in of the next one, right? And the very last one, the serial out, would be the one that connects to the Arduino, right? So these are the connections to the Arduino, and although there are 6 pins, one of them you actually don't need to connect it to Arduino. You only connect 5 of them, and then A, B, C, D to H. So these 8 pins are the inputs. So you would connect the buttons to these pins, right? However, if you notice, the pins are connected directly to the pins of the chip are connected directly to the pins where you would connect the buttons. And you cannot do that, because if these are not connected by default to something, and by something I mean either ground or VCC, via a resistor, you cannot just connect them directly. Well, actually you can, but you need to connect them to VCC or ground via a pull down or pull up resistor. That means that if you don't do that, if I was to connect this board to an Arduino and read what these pins are without connecting anything, this would float. And what that means is that they would go from 0 to 1 randomly, and they would not be in a default state. You need every pin to be in a default state. So you are, for instance, in a 0 state, and when you press the button, that goes to a 1 state, right? That's what you want to do, detect buttons. If you don't connect this to either VCC or ground, they will be floating, and they will be randomly jumping from 0 to 1. So the problem with these boards is that they are not just ready to go. You need to do something like this. See? So these are connected from the bottom. So there is a resistor, a 10K resistor in this case, anything from 5000K approximately. Sorry, I just hit the camera tripod. Anything from 500K and above should work. Default usually is 10K, but whatever you use in the thousands should work. These are connected to this line of pins here, and then to the pin, right, in series. And then this end of all the resistors, as you can see, they are connected together and then connected, in this case, to VCC, right? So what this does is that by default, all the pins in this shift resistor are going to be in a 1 state. And what I'll do is connect one end of the button, of 8 buttons, so one end of each button in one of these pins, and the other end to ground. And what that does is that by default they are in the 1 state because they are connected to VCC. When you press the button, since electricity goes through the least resistant path, and to be in the 1 state, they need to go through the resistor, but that's the only way they have at the moment. When you don't press a button, the only way they have is to go through the resistor. When you press the button, you close that contact directly with no resistance or very little resistance, and that makes electricity flow easier from the pin to ground. So that would change the state to 0, right? So yeah, these are very inexpensive, these are individual, and the problem that they have is that you have to build this kind of contraption. So this is a very good option, actually, if you don't mind doing this, and it's not too difficult of a build. But this is a very good option. It's a little bit bulkier because you can then cut this board like here and make it a little bit. I mean, I soldered this to a big board because I'm going to be using this for a different project, and I'm going to be soldering more shift registers here in series and connected them. But in this case, since you want this inside a Tira grip, you would need to cut this, right? So yeah, you could fit this, and it would still have enough space. You will need 4 of these in each grip. Actually, 4 in the left grip, 3 in the right grip, and then the 4th one would be inside the enclosure, outside of the right grip. But anyway, You could also do it 4 and 4. You will see that in the video, don't worry. Yeah, so that's actually a very good option. Any of these three. So this one, if you want to spend a little bit more money and maybe, I mean, these maybe don't fit in the grip, but you could also store all of them outside in the enclosure, outside the grip, inside the enclosure, and just run all the wires from the grip inside the enclosure. That's an option. So you could actually do that if you wanted. These are also a good option to build this. I think for me, this is probably of the three, maybe the first option, maybe. Yeah, I think I would go first, then second for the port expanders, and maybe this would be my last option, but it's still a valid option. In my case in particular, and you can do that as well, let me show you something. I have this. And what are these? Let me show you. These are custom-made PCBs that I designed and produced. This is essentially the same. It's a mix of this and this because it's an individual board, so you can have as many as you need. I did it so if you need several together, you can actually put them together and solder the two pads together. That would be actually like that. So you put a big blob of solder in between, and that way you can just run wires, whatever you want. But the thing is that these include a resistor so the pins on this custom-made board actually are pulled up in this case. So I prefer pulling pins up and have them all in state 1. I believe the designers of this board did it this way just to allow the user to choose whether they wanted to pull it up or down. So that way you don't choose for the customer. Like these ones, for instance, they choose for you. I'm not sure. I think these are pulled down. They already have, if you can see here, resistors in them. So they chose the pull down for you. So you cannot pull them up. That's perfectly fine. I actually think I would rather this had the same, that the designer said, we're just going to pull them down or pull them up, whatever option actually works. So I don't know why they left it open. It's either a bad design or they just thought the user would want to choose whether to pull it down or up. So what I did in this case is essentially a copy of this, but picking up the option. So when these are mounted, and notice these are SMD components, so you need to have a little bit of skills, an air gun or a hot plate to solder SMD components. But once you have built this board, this is all you need. There's nothing else. You don't need something like this with these ones. They already include the resistors. This is actually my first version, and it works. So it's tested. I've had TDACs built with this, and they work perfectly fine. But I have a better, an improved version of this board that I have not manufactured yet and not tested. But let me tell you the difference, and I will share both of them. So if you wanna try this option, this is a very good option, and this is the one that I actually go for usually. I'll be using this for a project just to, to use the ones that I have, but I'm not gonna buy more of this because I don't wanna have to do this. For me, it's way easier to use this. So, and the difference is that this footprint here, let me show you. So you can buy the components separately. This is actually the chip. And the problem is that this footprint here, although you can solder them, but it's not 100% the perfect footprint. So the thing is that this is a little bit too wide, and the legs just barely touch the pins. As I said, you can make it work, but the new version has a thinner profile, so the legs sit on top of the pins, which is what you actually want. Also, it's designed so So here you have 4 pins, and then I think it's 6 pins here. And these 4 pins are 4 inputs. These 6 pins are 4 other inputs and then 2 grounds, right? And these 2 grounds are the ones that you would actually connect the button to. So as I said, you have to connect one leg of the button to one of the input pins, and the other leg, which they are wrongly labeled here. It says J3 and J20, but these are ground pins. So the other leg of the buttons would be connected to this. And that's just so you don't have to connect them to these ones in here, because these ones are the ones that we are going to be using to connect them to the Arduino or to the next shift register board. You have the serial out and serial in pads here. So yeah, the improved version also has all the 8 pins in one side instead of having 4 and 4. And these are through hole. So my idea is that you could actually, let me grab another one. With that improved version, you could actually stack them together, and they would have a smaller footprint. So you would, and it would be something like this, because they are like stepped to a side. So there would be one connected here, one connected here, and one connected here, as many as you would need. And the pins would be a little bit more available because they would be protruding. But as I said, I have not tested those yet. I want to spend this first, and when I use all of them, then I'll build the new ones and try them. But you're free to try them if you want. So yeah, that's I think that's gonna be it for today. I hope I didn't confuse you more, which is possible. If you have any questions or any comments, let me know in the comments. I will gladly answer any questions. And yeah, so now that I've shown you these options to build the TDAC, I'm happy to announce that I will be building and recording the process very, very soon. So stay tuned if you want a TDAC for yourself. It's a great project. It's not difficult at all, and it can be really, really inexpensive. So yeah, stay tuned for that, and see you in the next one. Cheers.